All right, welcome. I hope you had a refreshing Easter. So it's been a while since we had the last lecture, and I was thinking that it might be a good idea to just recap what we did before Easter. One of the main topics that we were concerned with were these canonical transformations. So, whereas we usually, when treating a mechanical system and then applying the Hamilton formalism, use these generalized coordinates q and the canonical momenta small p, we saw that it was possible in general to make a transformation of phase space and introduce a new set of coordinates, large Q and large P. And if these coordinates satisfy the following equations, where K is the new Hamiltonian in the new set of coordinates, large Q and large P, well, then we were dealing with a canonical transformation. So it's important to distinguish a canonical transformation from an arbitrary transformation, because we can always generate some new function in terms of the old coordinates, but it's only canonical if these equations are satisfied. And we saw that in order to accomplish this mathematically, we can make use of a so-called generating function. Because we derive that from a modified Hamilton's principle, we had a specific relation that had to be satisfied for the old and the new set of coordinates. So we had the following relation. This extra term here appears because we can always add a total time derivative of some function f to the variation of the action without changing it, because this has no variation at the end points. So then we had to look at a couple of examples of this f that could be used to sort of establish a bridge between the old set and the new set of coordinates. And just to remind you, we also had a look at a couple of examples. Namely that if we chose the generating function to be of the second class, f2, and written in this way, then using the equations that couple the old and the new set of coordinates, we found that this actually generates the identity transformation. And we could generalize this statement somewhat. to consider a function like this. And we saw how this type of generating function would correspond to a point transformation. Like this, which is, for instance, going from polar to Cartesian coordinates. And one of the very last things we did before Easter was to consider a practical use of these canonical transformations. So all of this is fine and well, but what is the purpose of it? What can it be used for? And the example that we considered was that we wrote down a specific Hamiltonian. And I posed the question, what kind of physics does this Hamiltonian describe? And from its form, it was not familiar to us. But then we saw that by applying a canonical transformation on the coordinates of the Hamiltonian, we could recast it into a well-known form, namely the harmonic oscillator. So that's one practical use of these type of transformations, that we can sort of rewrite the problem in terms of something which is more familiar. Now, there's an alternative way to view this, which I want to show you here. So we'll again consider the harmonic oscillator, just to show the principle. So in one dimension, the harmonic oscillator Hamiltonian takes the following form, where P is the canonical momentum and Q here is the position coordinate. So now the point is the following. If it's possible for us to find a transformation that looks like this, then by direct insertion into the Hamiltonian, we get the following. So why is this good? Well, do you see an advantage of this Hamiltonian compared to what we started with? Is there any qualitative difference between them? Mm-hmm. So this one depends on small p and small q, whereas this one depends on large p. So what does that mean for the coordinate large q? It's then a cyclic variable. Now cyclic variables we are especially fond of, because that means that we have some symmetry in the problem, and hence something is conserved. So by means of this transformation, we're making Q, large Q, cyclic. So that would be pretty good. We would have reduced the difficulty of Hamiltonian because it now depends only on one variable. So then the question is, okay, is this transformation allowed? Will this work if we are to use the Hamiltonian formalism, for instance? Is it a canonical transformation? Because we need this to be a canonical transformation if we are to use Hamilton's equations on the new variables large Q and large P. So the question is this a canonical transformation? Well, we have a function here, f of large P, which remains unspecified so far. So the answer is that it depends on what f is. In fact, we have to find an f such that this transformation becomes canonical. We can't just choose an arbitrary f. So the task is to identify which f ensures that this transformation is canonical. Now, we can use the generating functions to actually identify what f has to be in order for this to be a canonical transformation. So the first thing we can do is to actually express one of the old variables solely in terms of one of the old, the other old, and one of the new. Because we saw that this generating function always depends on one of the old and one of the new variables. So we can express, for instance, P as follows, just by substituting f from the lower equation. And we're then in a position to identify which of the generating functions that will do the trick. So for instance, this equation here actually indicates that we can use f1. Because if you consider the equations that we derived, in the case of f1, we had, for instance, this as one of the three defining equations for the canonical transformation. So we see here that the expression for small p has exactly this form. It depends on small q and large q, just like this transformation equation, which is valid for f1. So by comparing these two expressions, we then obtain the following. Just as the simplest solution. So we're just integrating the expression over there with respect to q, small q. All right, so this is one part of the transformation, but we know that for each generating function we had three parts. We had two equations of this type, generating the old and the new set of variables, and we also had a third equation relating the Hamiltonians to any possible explicit time dependence. So the other half of the transformation between the set of variables looks like this. But we now have an expression for f1 due to the integration over there, so we just perform a partial generation of this one. And we're now in a position where we can actually identify what this function f has to be. And the way we can do this is to express q in this form and then read out what f has to be. So we have this. So our result is in that the function f has to be equal to the square root of 2m omega large P in order for our transformation to be canonical. So in terms of the new variables, we then have a appealing form of the Hamiltonian is just omega p. So it really doesn't get much simpler than this, a constant multiplied with one of the variables. Now, we do know that large Q is a cyclic coordinate, which means that due to the symmetry, we have a conserved quantity. So what is the conserved quantity for our specific situation? Any ideas? So how would we find what is conserved if we have a cyclic coordinate in the Hamiltonian? If we had a Lagrangian function where we had a cyclic coordinate, how would you find the conserved quantity? I see Easter has been tough on you.
Well, it has to be a partial derivative of h.
Mm-hmm.
And we could find the momentum.
Yeah. So in the Lagrangian case, we had this equation for the canonical momentum. So if Q is a cyclic coordinate, well then P is conserved. Correspondingly, for the Hamiltonian, we have Hamilton's equations. And one of them dictates that if H is independent of large Q, well then the belonging canonical momentum P is conserved. So we would use Hamilton's equations to show that P is conserved. So this is exactly the same procedure as in the Lagrangian case. We're just using Hamilton's equations. But I'm using a K, I'm not using H. But we have an expression for H. So how are H and K related in our case? Can we write down any simple relation between H and K? Well, keep in mind that from the generating function we obtain three types of equations. Two of them pertain to how we go from the old set small q and small p to the new set large q and large p. But the third one related the Hamiltonians. And the relation was that the only difference between H and Q would be
specific time dependence in the generating function?
exactly. And do we have such a time dependence?
No.
No. So we have h equals k. So I can just use this result immediately. Okay, so large q is a cyclic coordinate, large p is a conserved quantity. And if large p is conserved, well then h is also conserved. And this makes sense because since we have no explicit time dependence, we know that energy should be conserved. So let me write that. So in fact, large p, the canonical momentum, has a value which is equal to the energy of the system divided on the frequency. All right, so with this in hand, we can now try to find the solution for the other variable in the system, namely large q. So we know that, for instance, if we use the Lagrangian formalism and want to solve a specific mechanical system, the solution consists of finding the time dependence of the generalized coordinates. Then we know how the system will evolve with time. So similarly here, to solve the system and find how it evolves with time, we have to find p as a function of time and q as a function of time. So we've accomplished half of the goal. We have identified that large p is in fact a constant with time. So the next step is to find what is q. And the equation of motion is Hamilton's equation. Just like the equations of motion are Lagrange's equations if we use the Lagrangian. So we have this. And by inspection, this takes the simple form omega. And we can then integrate this equation to find the following general solution. Where this integration constant alpha is determined by the initial conditions in the system. So the solution of our system is that p is a constant and q is a linear function of time with a possible offset from the orgo in terms of alpha. Now, with these two quantities in hand, we can now substitute them back into our old set of variables to see if we are able to regain the known solution. So what do we know about small q, the position dependence for a harmonic oscillator? How should it look like as a function of time?
It's oscillating.
Mm. So it's a sine or cosine?
Yes.
Yeah. Okay, so let's check. We have this equation here. So that looks good. We have a sinusoidal function. So this is harmonically oscillating. Now in the same way we can also find P just by inserting Q here. So it could be useful just to compare the behavior as a function of time of all of these variables. So let's compare the old set of coordinates with the new set of coordinates and look at their time dependence. So what you'd find if you'd insert the new set of coordinates back into the small p, which describes the momentum in the original coordinates for the harmonic oscillator, you would find this, a maximum amplitude of 2m e, and then oscillating in the following way. Similarly, for the position coordinates, we know that it looks like this, so just assume that alpha is 0 here. So it corresponds to a situation where we at time equals 0 have the harmonic oscillator at the origo. So then we know that Q should look like this, with a maximum amplitude provided by this. So with increasing energy, the maximum amplitude increases as a root of the energy. And again, we can just briefly inspect these expressions to see if they make physical sense. So we see, for instance, that the maximum amplitude decreases with increasing mass, which is reasonable. The heavier the object, the harder to obtain a maximum amplitude. But the momentum, on the other hand, increases both with mass and energy. Okay, so that's the old picture. Now, in terms of the new coordinates, well, the canonical momentum is just a constant. It's the energy divided on the frequency, omega. And the position is just a linearly increasing function of time. So even though these two set of coordinates, the new set and the old set, have very different behavior in terms of their time dependence, they describe exactly the same physics. Now, from this analysis, we have perhaps seen a few technical, we've gained some technical insight into how we can do these type of transformations. But I would like to extract a more profound point regarding this. So with the two preceding examples, what we have seen as a practical usage of these canonical transformations is that they can be used to, one, recast a Hamiltonian from an unknown form to a familiar form. But secondly, as this example illustrates, canonical transformations can be used to make coordinates cyclic in a Hamiltonian. With all the advantages that follow from this fact. So what we saw here was that, in a sense, it's somewhat opposite to case one. We started out with a fully familiar form of the Hamiltonian. And then we cast it into something which probably was unfamiliar to us, a function squared of the momentum divided on 2m. So that was an unknown form, but it was simpler because we had one cyclic coordinate. So these are the main sort of insights in terms of what the canonical transformations can be used to. All right, we'll start with something which is known as Hamilton-Jacobi theory in quite a while, or in a little while. But before doing so, I'd like to introduce a mathematical tool which will be useful to us. And it's known as Poisson brackets. So the Poisson bracket associated with two functions u and v with respect to canonical variables q and p is defined in the following way. So one property that immediately follows from this definition is that it's anti-symmetric. And we'll have a look at a couple of other properties of this tool, and also how it is in fact related to so-called commutators in quantum mechanics. But we'll do this after the break.